We now look at one of an important equation in the fluid dynamic is the equation of continuity. The equation of the continuity is a direct consequence of the incompatible of the simple fluid. The point is that if you push an amount of fluid into the tube of flow, for example, if you put this amount of fluid into the tube of flow, the same amount of fluid have to flow out of the tube unless the density of the fluid in this region will increase in this region, okay, because you push an amount of fluid inside the tube of flow, the same amount have to flow out, and if not, it means that the density in this region will change, right? But we say that the fluid is incompressible. It means that the density is constant. You cannot compress the fluid. So it means that if the density here is constant, if you push the fluid here, it have to flow out. The same amount of fluid have to flow out here at the other end of the tube of flow. Okay. And in this figure, you can see that if you push the amount of fluid that have the thickness of delta x 1 and the cross-sectional area is A1. This is the A1, okay, into the tube of flow, and the same amount of fluid flow out of the tube of flow at the other end, but at the other end, at this end, the cross-sectional area is A2, and the fluid move at the distance of delta x2. Okay, you can see that we have that A1 delta x1 must equal to the A2 delta x2. Okay, it means that the volume of the fluid flow in and flow out must be equal, right? Okay. Now, if the time that you push the liquid into the tube of flow at the left end, here is the delta T, okay, the same amount of fluid have to flow out at the other end in the same time too, okay. We should have the time that the fluid flow out at this end is equal to the time that the fluid flow in at this end, which is equal to the delta T. Okay, so if we divide both sides of this equation by delta T, this is delta T2, but you can see that this delta x over delta T is the velocity of the fluid at the left end, the velocity of the fluid here, V1, and the delta x 2 over t. Delta t is the velocity of the fluid at the right end, and we call it V2. So we have that A1 V1 is equal to the A2 V2. This is what we call the equation of continuity. We can use this equation of continuity to explain many things. For example, if you go back home and you water your garden using the hose, like in this figure, if you let the water flow out normally, you may have the water that flow slowly, okay? But if you want the water to flow faster, okay, maybe because you want it to go farther, you have to place this end of the hose, okay, to make the area, the cross-sectional area smaller. And you can see that from the continuity equation. If you have a flow, if you have flow in a tube like this, on the right part it has the cross-sectional area A1, and on the left part it has the cross-sectional area A2. Clearly here A2 is less than A1. But if you look at the continuity equation, A1 V1 must equal to A2 V2. So the consequence of this is that V2 is larger than V1 to make the continuity equation valid, that the product of A, V is a constant. Okay, so we have V2 is larger than V1. That's why the water moves faster when you compress, or when you reduce the cross-sectional area of the host. Okay, there is also another interesting phenomenon that related to the continuity equation. If you notice that when you release the water from the tap, okay, if you have a tap like this, and you may have the valve here, okay, you have the valve here, and you release the water, and if you not let it move so fast, too fast, you will see something like this. That is, the cross-sectional area of the water becomes smaller when it flows downward. This can be easily understood by the continuity equation, because you can see that if you look at the cross-sectional area, here is A1, and the cross-sectional area here is A2, and if the velocity of the water here is V1, and the velocity of the water here is V2. But in this case, you can see that the water moves down under the gravitational force, so it has the acceleration A equal to G. So it means that V2 is larger than V1, and from the continuity equation, you have that A2 is smaller than A1, so that Y we have the flow from the tap like this. This is an example of using the continuity equation.